I'm Jeroen van Meij, and welcome to my lecture series on computer and network security. In this third video on asymmetric encryption, I will delve deeper into RSA and explain how a computer can efficiently perform RSA-related calculations. There are actually two aspects related to RSA where efficiency is important. The first one is the encryption-decryption process, and the second one is key generation. But let's start with encryption and decryption. In encryption and decryption in RSA, there's a need to raise an integer to a specific integer power modulo n. If the exponentiation is done before reducing by modulo n, the value can become extremely large, resulting in integer overflows when doing the calculation on a computer. However, the properties of modular arithmetic can be used to reduce the complexity and reduce the size of intermediary results. This property is that a modulo n times b modulo n equals a times b modulo n. That means that we can already take the modulo of intermediary results and end up with the same solution as when taking the modulo only at the end of the calculation. This reduces the size of the intermediary integers in the calculation. Second aspect is the fact that we need to calculate large exponents. For example, in encryption, we need to calculate m to the power e, where e can be a very large number. We can, however, reuse intermediary results when doing such exponentiation. For example, here you see x to the power 13 equals x times x to the power 4 times x to the power 8. We only need to calculate x modulo n, x square modulo n, x power 4 modulo n, and x power 8 modulo n, and then reuse previous values. So by calculating only these four values, we can calculate x to the 13th modulo n. Using these two properties, we can come up with an efficient algorithm for modular exponentiation, or to calculate a to the power b modulo n. Before I explain the algorithm, let's take a look at how we can express b. We can express b as a binary number consisting of k plus 1 bits. Given that each bit is either 1 or 0, we can then write b as the sum over all bits bi multiplied by 2 to the I power. Or, since bits are either 1 or 0, sum over all bits bi different from 0 and then take 2 to the I power. This obviously equals the value of b. So, as a consequence, we can rewrite a to the power b as a to the power of this sum. And since a sum of an exponent can be written as a product of a to the power of each of these elements of the sum, we end up with the product over all bi different from 0 of a to the power 2 to the ith. Then, given the fact that in modular arithmetic we can take the modulo of intermediary values and end up with the same result, we can take the modulo of n of each of these intermediate calculations, each of these powers of a to the power 2 to the ith, and end up with a way to calculate a to the power b modulo n, where our intermediate value will never become higher than n. This formula can now be converted into an algorithm that can be implemented on a computer, and it looks like this. We use a temporary variable f that stores the intermediary result of this exponentiation and multiplication. So, each iteration, starting from k down to 0, we look at one bit of b, starting at the most significant bit, going to the least significant one. Then we multiply f by itself modulo n. If this bit bi equals 1, we also multiply f by a modulo n, and after the loop we return f, which will then contain the result of a to the power b modulo n. This algorithm is very efficient and avoids overflows of integers, as during each intermediary step of the calculation we calculate the result modulo n. And to make sure you all understand this algorithm, I have an exercise for you. Use this modular exponentiation algorithm to calculate 7 to the power 21 modulo 127. Good luck. You may have noticed that the number of multiplications modulo n that need to be performed in the modular exponentiation algorithm depend on the number of 1 bits in the exponent. The more 1 bits, the more multiplications, the more complex the algorithm is to execute. So, for doing RSA encryption, it makes sense to choose an exponent e of the public key with as few 1 bits as possible to make the encryption process as efficient as possible. Therefore, the most common choice for e is 65,537, which equals 2 to the 16 plus 1. Other popular choices are the numbers 3 and 17. All of these only have 2 bits equal to 1, and thus require very few multiplications to perform modular exponentiation. However, for small values of e, RSA is very vulnerable to some simple attacks. For example, assume e equals 3. Some sender wants to send the same message m to 3 receivers. He uses e equal to 3 and then a different n1, n2, and n3. An attacker is able to intercept e, n, n1, n2, and 3, which are all public, as well as the 3 ciphertexts c1, c2, c3. In this case, the attacker is able to derive m by calculating the cube root of m to the third, which is not that hard. This problem can be solved, however, by adding a unique pseudo-random bit string as padding to the message m. The calculations using e can be made more efficient by choosing a specific value of e which has few 1 bits. However, if we choose e, we cannot choose d. We need to calculate it as the multiplicative inverse of e. Moreover, small values of d are vulnerable to brute force attacks and cryptanalysis. As such, we need to find an efficient way to calculate c to the power d modulo n for large values of d, as they are more secure. We can now use the Chinese remainder theorem to make this calculation more efficient, in case d has many 1 bits. Let's start by defining two intermediary variables vp and vq, equal to c to the power d modulo p and c to the power d modulo q. Applying the Chinese remainder theorem, we can now state that m equals vp multiplied by xp plus vq multiplied by xq modulo n, where xp and xq equal q times q minus 1 modulo p and p times p minus 1 modulo q. This can be easily derived from the Chinese remainder theorem, given the fact that n equals p times q. Now, using Fermat's theorem, we can derive that vp also equals c to the power d modulo p minus 1 modulo p, and vq equals c to the power d modulo q minus 1 modulo q. The value d modulo p minus 1 and d modulo q minus 1 can actually be pre-calculated, as d, p, and q are known in advance. By doing this pre-calculation, this calculation of m is about 4 times more efficient than the original calculation of c to the power d modulo n. So now that you know how to efficiently perform encryption and decryption with E and D, we can take a look at how we can actually go about and efficiently generate the public and private key. To generate these keys, we need two prime numbers P and Q, which are multiplied to obtain N, and then need to select E or D and calculate the other. So the first step towards generating an RSA key is to determine two large prime numbers p and q. Any adversary can know n as it's part of the public key. He also knows that n equals p times q. So to prevent a brute force attack, where the attacker is able to derive p and q from n, p and q should be large enough. Moreover, the method of founding two such large prime numbers should be efficient. In general, this kind of method is used, where first some random uneven number is generated with the desired order of magnitude, meaning with the desired number of bits. Then some check is performed to see if this number is prime. As it is computationally very difficult to calculate with certainty whether a very large number is a prime or not, some probabilistic method is used. An example of this includes the Miller-Rabin algorithm. Such a probabilistic method will give you a certain percentage probability whether or not a number is prime. Usually enough tests are performed to make sure that this probability is very high and close to 1. If the number is considered prime, it is returned. This process can be repeated for generating both p and q. Once we know p and q, we can easily calculate n as a product of p and q. Since p and q are primes, also the totient of n can be easily calculated as p minus 1 multiplied by q minus 1. Subsequently, we need to select either e or d. Assuming we will select E, we can then calculate D from E. As I mentioned before, a good rule of thumb for selecting E is to make a choice with as few 1 bits as possible. For example, 2 to the 16th minus 1. Then we can calculate D as the multiplicative inverse of E modulo totient n. We also need to make sure that the greatest common divisor of E and totient n equals 1. So they are relative primes. Luckily, we can do both things with a single calculation. Namely, by using the extended Euclid's algorithm, we can calculate the multiplicative inverse and make sure that the greatest common divisor equals 1. A possible strategy is to select random numbers of E until one is a relative prime of totient n. And if one wants to make this the encryption efficient, one should select random numbers of E with few 1 bits. And to finish this video and give you a better feeling of how this process of selecting E and D works, I have an exercise for you. Given P and Q equal to 7 and 11, determine the highest suitable value for E and calculate the associated value of D. You can use the formulas displayed on the left and use the extended Euclidean algorithm, which is summarized on the right. Good luck! In my next video, I will talk about attacks against RSA.